All right, hi. So these were some problems that were. Hi, everybody. These were some problems that were asked for honors physics, chapter 2, problems 16, 28, and 29. These were asked to do solution videos for, so here we go. Number 16, it says a somewhat idealized graph of the speed of the blood in the ascending aorta during one beat of the heart appears as in this figure right here. And then it says approximately how far in centimeters does the blood move during one beat. So I'm assuming this is one beat right here, and I see that it's a velocity versus time graph. So how do I find out how far something moves in a velocity time graph? Well, that's the area under the graph. So I'm looking for this area here. I can see that it's a triangle. So I'm going to do, so for this, it's going to be, the area is going to be 1/2 base times height. So that area is going to be 1/2. The base looks like about 0.2. That's 0.4 minus 0.2. So I'll say 0.2 seconds multiplied by the height, which is about like right here. And I'm going to guess it's about 0.75 meters per second. So 0.75 meters per second. So that area, the seconds cancel out. And I get 0.5 times 0.75 times 0.2. So let's try that. 0.5 times 0.75 times 0.2. And I get 0.075, but if I round that, that's in meters. If I round that to centimeters, I would multiply that by 100. Well, that's 7.5. 7.5 centimeters times 100. Can I do, here, I'll do my answer. There we go. All right, so this is going to be 7.5 centimeters. All right. Next up, it says, assume similar data for the motion of the blood in your aorta and make a rough estimate of the distance from your heart to your brain. Estimate how many beats of the heart it takes for blood to travel from your heart to your brain. So answers are going to vary here. I could look at my heart to my brain. I want to say like a 1/2 meter, maybe. So if I want to say like a half, I'll say a 1/2 meter. So I'm going to say the distance is a 1/2 meter. So how many beats would that take? Well, in one beat, it's 7.5 centimeters per beat. So if my distance from my, so again, I'm doing this. My leg's really small. My arm is really big. And so we're going to say this distance is about 0.5 meters. That's 50 centimeters. So if I have a 50 centimeter length, then I could do some unit conversion by putting 7.5 for one beat, and that'll tell me how many beats that I will get here. So centimeters cancels out, and 50 divided by 7.5, and I'm getting about 6 or 7 beats, so about 6 to 7 beats. Again, this is approximate, so answers are gonna vary here. So about 6 to 7 beats to get the blood going to my hand. I have freakishly long arms, what can I say? Okay, so next up is number 28, which, geez, look at that thing, it's terrifying. Let's not look at you for a little while. When jumping, a flea rapidly extends its legs, reaching a takeoff speed of 1 meter per second over a distance of 0.5 millimeters. The reason I wanted to bring up this this image here is so you could see its legs and what we're talking about when we say that it jumps like that. It has a takeoff speed of 1 meter per second, and it does that over a distance of 0.5 meters. So I'm going to say we're going to assume that the flea is at rest on the ground. So the flea is at first on the ground, its legs are collapsed, so it kind of looks, I guess, something like that before it goes to leap up, and then it's got its legs out. So at first it's collapsed, but then it goes a distance of about what they're saying. They're saying a distance of about 0.5 millimeters, which is times 10 to the negative 3 meters. Again, you can convert that. And at this point, when the flea is here, after it's launched up, so it'll have some final velocity of 1 meter per second, where its initial velocity is 0. Okay, so there we go. That's kind of my diagram here. At first, the flea is on the bottom here, and then it's up top right here. So I'm going to say VOVAT. At first, it's at rest, but then it has a velocity of 1 meter per second. Does this over a distance of 0.5 times 10 to the negative 3 meters. So I can find out its acceleration using alpha. Initial velocity is 0, so I can isolate acceleration by dividing both sides by 2d. So these cancel, and then I get v squared over 2d is equal to my acceleration. V squared is 1.0 squared divided by 2 times d, which is 0.5 times 10 to the negative 3. And I get my acceleration. Let's see. 1 divided by 0.5, 2 times 0.5 times 10 to the negative 3. So it's going to be 1 squared. Alright, I'll say squared. Why the heck not? And then that answer divided by 2 times 0.5 times 10 to the power of negative 3. Oops. To the power of negative 3. And I get 1,000 meters per second. Yikes. That's a lot of acceleration for one flea. So there we go. That's part A. And then lastly, it says, how long does it take for the flea to leave the ground after it begins pushing off? So basically now I'm just looking for time. I'll just use omega. That's going to be the easier one to use. Again, the initial, so nothing's changed. They're just asking me for the amount of time. The initial velocity is 0. So I get the velocity divided by the acceleration is going to give me the time. Final velocity is 1.0. The acceleration I just found is 1,000. So the time then is going to be 1 divided by 1,000. It's going to be 0.001 seconds. Nailed it. So then this last problem says a car traveling at a speed v takes a distance d to stop after the brakes are applied. What is the stopping distance if the car is initially traveling at a speed of 2v? Assume that the acceleration due to the braking is the same in both cases. So I will assume that because that's pretty much true. So at first it's got a speed v, travels a distance d, and then they're saying, all right, then it's traveling at speed 2v. What's the new distance that it's going to have? And I'm going to assume, so I drew out my diagram here ahead of time. I'm going to assume that the distance is going to be greater if I'm traveling at a greater speed. I can imagine if I'm traveling at a greater speed and I slam on the brakes, it's probably going to have a longer stopping distance. The question is, how much longer is that stopping distance? So this is what I call a ratio problem, and I think that's the what I tend to prefer ratios because to me it's more mindless. I just take the ratio of these two equations, these two situations, and then the math solves the problem for me. But I'm going to try and also show what you could do, which is do it using a kind of looking at the equation and trying to figuring out holding all other things constant. This is a little more sophisticated, but some students might find it easier. So again, I got situation A and situation B. Situation A is where I'm traveling at speed v. That's right here. So I'm saying v naught is equal to v. So my final velocity, which I'll say is a actually. So I'll say this is v naught a. This is VA, this is AA. So all of these are for situation A. And this will be DA. So using that now, this is all situation A stuff. So my initial velocity, they told me, is V. That's what they gave me. My final velocity is going to be 0 because it comes to a stop. The acceleration, I'm just going to say it's some constant A, because they're saying the acceleration is same in both cases. So dA then, I'll leave it as dA, but I know dA, and so then I ask myself, what equation do I know that involves those four things? Well, let's also do situation B. So situation B, I'll say this is the acceleration for situation B. This is the initial velocity of situation B, the final velocity of situation B, and then the distance traveled by situation B. So my initial velocity is 2v. My final velocity is also going to be 0 because we're talking about the stopping distance, so at the end it's going to stop. The acceleration is also going to be, I'll say negative a. Sorry, this should also be negative a. So we're saying that, okay. And then the displacement, I mean that I know, but that's what we're trying to find. So again, I got those four variables, and the question is, how can I relate these variables? And the answer is through alpha. So I got v squared equals v naught squared plus 2ad. And so both situations, the final velocity is 0. And then I could subtract both sides by v naught squared. And I get negative v naught squared equals 2ad. So basically so again, they're saying that in both these situations the acceleration doesn't change. So I can then think, all right, if I double this, that's pretty much what we're doing here. We're doubling the initial velocity. How would that change the distance traveled? So if I double this, because of this squared term here, it's going to quadruple my distance. So if I made this 2 times the amount, so if at first if it was 1, well then the distance, if I assume this is also 1, then the distance is going to be 1 meter. But if I then double it, so it's 2 squared, then the distance is going to be, so that'd be distance of A, the distance is going to be 4 meters. So that's kind of a way I could look at it there. But this is why, you know, if things get more complicated than this, then I would, you know, I find myself kind of just in my own head. So what I like about doing the ratios is that I always do situation B divided by situation A. So I take this same relationship here. So so using this and using the fact that they are at rest at the end, both of them do this, right, over here and over here. So I'm going to take the ratio of this relationship that I found here. So it's going to be situation B, so negative v naught b squared equals 2ab db. And then I take the ratio, so it's going to be negative VA squared so I'm just making these equal and finding the ratios, 2 AA dA. Okay, so now I'm going to plug in what I know. In situation B, the speed is 2v, the acceleration is negative a, and the displacement, that's what I'm looking for. Then it's going to be v squared for situation A, divided by 2 times negative a dA. Negative cancels out here, negative a cancels, 2 cancels. Let's clean this up a little bit here, because this squared is gonna distribute. So this is gonna be 4v squared divided by v squared equals dB over dA. V squared cancels out, and I'm left with 4 equals dB over dA. So I get 4 dA is equal to dB, or essentially saying that the new distance is 4 times the original distance. Yeah, if you double your speed, it's something to think about for driving. If you double your speed, your stopping distance becomes 4 times as great as if you were your initial speed. Alright, so hope that helped, and bye.